we'll finish off with the Bernoulli equation before we move on to the next topic. We'll start next week. All right. These two things, since we are still talking about Bernoulli equation, might as well talk about the flow measurement lab that you did now. Okay, and how you need to process the data. All right. Okay. So, and then after that, we'll talk about energy grade line and hydraulic grade line, which is the most advanced topic of Bernoulli. So if you hopefully understand what's going on up to now for the Bernoulli equation, then you can figure. Then this one will make some sense to you. Okay. So remember you did the lab or not? You did with me, All right. There were two rigs there. All right. One was with the 8 columns. All right. That one's the Armfield. All right. Okay. So this is your lab report. Okay. If you filled up this top 8 here, all right, this is your page. If you filled up this top 8 half of the graph here, then you did it on the Armfield rig. Is that okay? All right, that's the one with the 8 columns of water. If you did it on the other one, then that's this Didacta Italia one. That's the one the a bit bigger one. All right. So in both cases, all right, you measured volume and time. Okay. All right, you measure volume and time. So you divide the volume by the time. What do you get? The volumetric flow rate. Okay, so that one is Q actual equals to volume over time. So for each data point, all right, you know what the Q actual is already. Okay, that's more or less should be accurate, unless your only error maybe your response time lah. Okay, in your stopwatch or your volume thing, but should be relatively accurate. All right. You can also compare this. All right. Remember we had a rotometer. All right. So you could plot Q rotometer over Q actual. Hopefully you get a line like this. All right, with all the data points, but it may not be like that lah. All right. Rotometer normally not so accurate. Alright, it's only Alright, so if you don't get a perfectly straight line, don't cry. Okay, it's not going to be that fantastic. It's not going to be that bad, but may not be that good. Okay, alright. Yesterday's equation, anyone remember? This, the one if you use yesterday's equation, which took the measurement of pressure and estimated the, what do you estimate? Estimated the flow rate. All right. Okay. Since nobody remember, I have to pull it back out. Where is it? Okay. All right, I pull it back out here. All right. Everybody have no problem opening these files. You run Windows. Those run Mac, then a bit of problem. Okay? Anyone run Mac? I may not open your iPad and all that, but I think can open iPad. Anyone try it? Right? If you run Windows 7, normally no problem. Except maybe Windows 7 Home Basic, I think may not have the notepad, the touchscreen parts on that. Okay, so yesterday's flow rate, this one. Okay, I copy. Okay, we worked out yesterday. That's the flow rate. If you just use the pressure measurement, okay, this is your flow rate. This is the ideal one. Okay, for each, no need to copy here. It's yesterday's one. I think there's a square root missing here. All right, for each of them, Alright, I think the D1 is the bigger diameter, D2 is the smaller diameter. Alright, for each of them, you can, each device, if you measure the pressure, you know what the flow rate is. Alright, for the arm field rig, alright, the first one is the Venturi tube. Venturi tube. I think that one is, I told you H1 minus H2, isn't it? Or is it H2 minus H? Doesn't matter, the absolute. P1 minus P2 equals to rho G H1 minus H2. Alright? By right, this is rho water minus rho air. G H1 minus H2. Alright? Why air? Because the manometer, one side is water, the other side is air. But if you don't minus the air, it makes no difference because density of water is about 998, density of air about 1. If you had 1,000 ringgit and you lose 1 ringgit, you won't cry also. Alright? So it's not too big a concern. Okay? For the orifice plate, alright, P1 minus P2 is equal to rho W minus rho air G H7 minus H6 or H6 minus H7, I'm not sure. Alright, but whichever it is, it's the absolute. Okay, the absolute. Alright, because it's only the absolute pressure drop that we are concerned with. Okay? Alright? Is that okay or not? Alright? Those? Huh? Oh, sorry, it should be rho air. Okay? For those that deal with the what do you call it? For those that did with the deductor rig, alright? I think the Venturi tube is one. Okay, then you did this one. By right, your Venturi tube had a mercury manometer. So mercury manometer, on the mercury manometer one, you do P1 minus P2 equals to rho W, rho mercury minus rho water. Alright, G delta H. Okay, whether that be H1 minus H2, H2 minus H1, that's the absolute value. Alright? Because the mercury, on one side you have mercury, the other side you have water. This one is made more significant. Alright, because rho mercury is around 13,600, rho water is around 998. So it's quite significant. Okay? Cannot throw it away. So around 8% or whatever. Okay? For the orifice plate, P1 minus P2 is equal to rho mercury, rho water minus rho air, rho water minus rho air, G delta H. Okay, so that's the main variable that you measured. You put in there, you can predict your Q ideal. Okay or not? Alright? The other problem is all this D1, D2 and all that. Okay? Yeah, this one right over here. Yeah? Cut this one out. Go to next page. Insert, new page. Paste it here. So not okay. What was I saying? Yes. The D1, D2, okay, it's all given here. Alright, I think they're accurate now. Okay, no, they're given here. Alright, in the lab handout, depending which one you do. Okay. Upstream diameter is the D1. Downstream throat diameter is the D2 for each of the devices. Alright, for Venturi tube, Venturi meter, orifice plate. For both arm field and deductor. So you choose which one you use. Is that alright? Okay, D1, D2 from here. I won't write it again. Okay. and paste. I don't know. Copy. Oh. Okay. Okay. Alright. So you can use this one. Let's save this one. And so for each case, alright, you can work out a discharge coefficient. Well, they call it CV lah. Obviously I call it CQ, but anyway, same. Discharge coefficient is equal to Q actual over, is it the other way around? Actual less than, right? Alright? Should be less than 1. I think it's the first way, isn't it? Actual less than ideal. Alright? You can work out a discharge coefficient. Alright? And for each case, you can also plot out the Reynolds number. The Reynolds number is equal to rho VD on mu. Alright? Which is actually rho V is actually Q actual over pi d1 squared on 4. That's the area. Alright, rho V, D is D1 over mu. Mu, you take water at about, what temperature was it? Yeah, not that important, about maybe 30 degrees. Maybe about 28 degrees. Alright, I think it will range between about 27 to about 31 like that. I'll take 28. Alright, in this experiment, the mu not so important, but in the pipe flow experiment, the mu is more important. That's why we were measuring temperature there. Here we didn't bother measure temperature. Okay, so let's save this one. And how you get this one? If you look up here, mu at 28 degrees. 28 degrees, which one is mu? I think it's on. Alright, 0.000833. Okay, dynamic viscosity. Okay, so one equals 0.000833. I don't know what the units are, the SI units. Okay, units here, kg per meter second. Alright, is that okay so far? Alright, so for each case, alright, the Reynolds number may not be the same for both the orifice plate and the venturi tube because the D1 is different. Okay, so for each case, you work out the Reynolds number. Alright, okay, I write a note here. RE can be different. See, D1 not same. Oh, if you did unfill, then the D1 same. You're lucky. There's only one Reynolds number. If you did this one, there's two Reynolds number because it's based on D1 and D1 not same. Okay, RE can be different. All right. For what do you call that? For both, even with same one, same Q. All right. So at the same Q, if you have different D1, in case of the ducta Italia, then you have two different Reynolds number. Which one water, which one mercury? Yeah, deductor. Venturi one is the mercury one. Right? Any questions? So for each flow rate, you can work out the CV, you can work out a Reynolds number. Okay, not so far. Alright? Okay. After that, finally, you are supposed to plot. So some of the data points might be over this side, might be less than 1,000. Okay, just plot. Okay, so this graph available from the lecture slide. It's actually from the textbook, but available lecture slide which you can download from Moodle. I think lecture 13 or whatever from Clayton. Okay, so you can get the digital copy. Don't need to scan and then play around. Okay, you can copy out the lecture slide and paste in your report. Alright, but And then on here, you can plot my data points are maybe here 10 to the 3 or something. All right. Okay, extend out a little bit. Maybe my data points like that. Hopefully they are like that. Then you can comment. But I don't think you go so high. Maybe like this. All right. Is that okay? This is for the what do you call it? Orifice plate. No, Venturi. Okay. Hopefully your CQ will be very high. Some people, their CQ might drop to about 0.91, 0.92, 0.9-ish, 0.89, but shouldn't be too low below that. Okay? If you're getting your CQ well below that, then check your calculation or discuss with me or the tutor. Something's gone off. Okay? That's for the Venturi tube. Venturi tube is the gradual one. That's why the losses very small. See the discharge coefficient nearly 1. Ideal and actual are nearly the same. Okay? So, and then you can discuss how well it compares and so on. This is this is the one that other people have done, and this is what they expect the range of C discharge coefficient to be. Okay. So even if you didn't make any correction, your error is also about, at high Reynolds numbers, your error is only around 2%. So correction, C discharge is quite small. All right, for here, the difference is quite big. All right, that's why the ratio is about only 0.6-ish. Okay, you need to work out your first, again, same. If your data go down to 10 to the 3, all right, you plot your points, something like that. Again, you'll be in a very narrow band, because although we vary the flow rate quite a lot, the Reynolds number range didn't actually change that much. Okay, so you may not get so high, maybe like that. Maybe. All right, and then again, you can discuss and compare. Which graph to compare to depends on this one. This ratio is actually your D1, your D2 over D1. Okay, which in, let's see what your case is, which is either 0.3175 over 0.02 over 0.03, which is equal to either 0.02 over 0.03175. This is for Armfield, or if I 0.02 divided by 0.05, 0.02 divided by 0.05 for Italia. So this one is actually, it's around 0.4. So you should, ideally you should follow this line in a perfect world. Okay, this one is about what? What is 0.02 divided by 0.03175? 0.6. .63. So, no, can't be 0. Alright, 0.63. Okay, so this one around here, between 0.6 and 0.7, somewhere. If your data is in here, that's good. Alright, if it's not, okay, then you can discuss why. Any questions? So, if you want to start at working out the flow measurement, processing the flow measurement results for the experiments, you can go ahead. This report only due in week 9. Week 9 Monday holiday, so maybe week 9 Tuesday. Week 9 Monday is 916 one. Malaysia Day. Okay. This semester long holiday, nearly 5 days. So out of 12 weeks, nearly 1 week holiday. Right. Any questions? Right. So I'll save this one. All right. So you have a go at calculating it. You most likely, if you make mistakes and all that, that's okay. We can discuss that. All right, and make the corrections. Okay. Any questions on? All right. what was I supposed to do? Yeah. Okay. EGL, energy grade line, and HGL, hydraulic grade line. Okay. Basically, P, I write in this way on rho G because it's in terms of height, plus V squared on 2G plus H in terms of height equals to constant along streamline. So if we have a tank, all right, let's assume our streamline starts from here. Okay, what energy does the flow have at that point? Nothing much, isn't it? Okay, so normally we have some datum, say, okay, some datum below here. Here H is equal to 0. All right, you can choose any arbitrary datum you like. Okay, so at that point, this point, what's the pressure? PATM. And normally we write in terms of gauge pressure, so that one just put to 0. Okay? So, and what's the velocity? 0. So this point, alright, if I were to plot this, this is actually your EGL right here. If I have to plot this creature, it's just be H. Right or not? This stationary point here is H. So this value here and this value here is H. So the line starts here. Alright, EGL, maybe EGL line I plot in blue. So the EGL line starts here. Okay or not? EGL is energy grade line. Alright? Is that okay? Hydraulic grade line. Then we have a pipe. Pipe go up, down, up, down. Maybe it's just like that. Okay? Is that okay or not so far? Alright? So once the fluid starts, so this is the streamline I plot in green. Streamline. So this creature is constant along that streamline. Assume no losses. Alright? Assuming no losses, this creature is this creature, which I mean this P over rho G plus V square 2G plus H is constant. Okay? So by right, the energy grade line should be constant. Should be blue. It's the EGL. Alright? The hydraulic grade line is only this term. H. What color should I put? HGL is equal to P on rho G plus H. Only the static part. Alright? So initially, if V is 0, this one also here. Okay? Or the same spot. Alright? Also here, in the top. Is that okay? Alright? So far? Then, what happens? Got velocity in the pipe, isn't it? Okay? So there will be a difference. It will drop. Okay, it will drop. This difference here, this height difference, is essentially V squared over 2G. Alright. It's HDL like that. I made a mistake. Let me check. Alright. No, my counterpart cover that part now. Maybe covered earlier. Yeah. No, you didn't cover that one. Yeah. I believe it's correct. Okay? So, this line is always the difference between, so this line is always the difference, alright, between the velocity, alright, V squared over 2G. So, in this case, although the pipe does this funny bend, alright, the HGL will just be, if the velocity is always constant, this will be HGL. Okay? The other component, if you, what? It dropped because some of the, alright, the question in front here is why this here drop. Actually, the drop is a little bit earlier. Okay? The drop is because the sum of this energy has converted to kinetic energy. Alright? Some of this, initially is all potential energy. Some of that potential energy is converted to kinetic energy. Right? Okay? So, within the HGL, okay, obviously there's two components, the pressure and just the elevation. Okay? So, if you, how to draw that? Let me draw this. Okay, so at any point, the elevation is here. Okay, that's your elevation. Huh? Actually, I draw wrong already lah. The HGL should be, the HGL should be at the level of the pipe. But I'll show that soon. Okay? Alright, don't panic. Okay, so far, you got the blue one is the elevation. Alright? So, this difference here, alright? So, you're okay with the blue one is the elevation, huh? Alright? So, what are our colors here? The gray one, this difference is P over rho G. Is that right? So this is so at any point, this is H. Okay. At any point, the blue line is H, the gray one is P over rho G, and the other one is V squared over 2G. they add up together because no energy loss. Yeah, is that okay? So at this point, are you okay with this point first? Alright, okay or not? Alright, at this point, alright, the pipe goes above the level. So this is our H, this is our V squared over 2G. Okay. Okay, V squared over 2G, normally I draw in purple. This is our V squared over 2G. Alright, this one, our gray part, P over rho G is actually negative. Alright, to get to the final line, we have this. Sorry, this one's correct, this one's wrong. P over rho G, this is actually the P over rho G. So we have this minus this plus this to get rid to the EGL. I repeat again. We start from here. Okay, we have the H, we have P over rho G, we have V squared over 2G. Okay or not? They add up together is your EGL. Alright? Here, we have H, we have P over rho G must be negative, and then V squared over 2G back to the EGL. Okay? What it means by P over rho G negative, because in this case I'm just using, what do you call it? I'm using gauge pressure. So a P over rho G negative means that your pressure is just less than atmospheric. So if you had a hole in the pipe here, air will actually get sucked into the system. Alright? This is like a cistern or like a siphon. Alright? So air will actually get sucked inside here. Is that okay? Alright? So here the P over G is negative going back down. Okay, here by right, yeah, here's where I need to adjust a bit. Okay, I undo. Alright. What color is this? So yeah, purple. Okay, here is still V squared over 2G. Okay or not? Then you would think here is the color wrong also. You would think here is P over rho G. Okay? But okay, that's okay, but some I realize, hey, hang on, your pipe open out the atmosphere already. Okay? So I got your P over rho G must be 0. So that part I wrote the pipe wrong. So by right, if this was still the case, the pipe should exit. Should I exit here? Should continue a little bit and exit here. Alright, if not, it doesn't make sense. Okay, so over here, okay, the blue, this is H, and this is V squared over 2G, and in this case, P over rho G should be 0 because it comes out atmosphere. Alright, exit to ATM. Alright, that's why my mistake, I'm sorry. Okay, so the pipe cannot exit down there. If I exit down there, then the system not in equilibrium. The pipe must exit basically at the HDL like that. Because the atmospheric pressure should be 0 at that point. Is that okay? Yeah? Yeah. In other words, if I didn't modify the pipe, the HDL line will have to be brought down. Then I have to redraw everything. And which means the velocity coming out of the pipe will be stronger. In other words, it's so logical. If you have a tank and a pipe, the lower you bring the pipe, the more higher the flow rate. Right? As you bring the pipe down, lower elevation, higher flow rate. Okay? That's what it means. Is that okay so far? And finally, Okay, so we done. Later you can try to combine the two lah. Next we'll do one with different pipe thickness. Okay. How many thickness you want? 2, 3, yeah? Okay. There are more examples in your textbook, alright, if you want to, but I don't want to talk too much because let you digest this information first. Okay, come out. Okay, here's the water level. Alright, so 3 different diameters. Alright, again, by right, EGL should be the same. Okay, by right, now that we're smart, we know HGL should end here. This should be a HGL, should end here. Okay, each time, so yeah. This one draw straight line lah. Okay, this one. So initially we start here. Okay, then we only drop a little bit. Alright, because here the V is quite low, so V squared over 2G. Okay. Then after that, we drop some more because we are going faster. So the V square of 2G is getting bigger, more kinetic energy. And after that, we drop further. So we exit here. And this is V squared over 2G. And it comes out. Okay? Here, normally I keep color consistent. So this point over to some datum. Okay, this is H. At this point, H is always this point anyway. Okay, H. I didn't draw the streamline. The streamline would be like this. We have started here. Okay. All right, and therefore your pressure. What's your color? What color is pressure? Gray color pressure here. All right, so we have still store some pressure here, and pressure getting less. And here, this point here. What happened to H? This is H, and P over rho G equals to 0. Okay, so that's the energy grade line, hydraulic grade line, the height, and that's different. That's the pressure. Okay, so that's how you draw them. Okay, you need to look pressure H and V square over 2G cannot go negative. All right, normally, if H go negative, maybe you should move your datum below. All right, P over rho G, if you are writing in terms of atmospheric pressure, that one can go negative. All right, so I did 2 simple examples for you. There are further examples which you could read up or look in the notes. All right, there are pipes going this way, that way, and so on. All right. All right. Okay. Sometimes you might have to draw them. Okay. Okay. Any other questions? Any questions? If not, I guess we finish a little 5 minutes, 5-10 minutes early. All right. You guys can work on your lab reports and other things. Well, no point. We'll start the next topic now. We'll start it on Thursday. Okay. So say. Oh, I'll upload this one. So if you haven't copied, it's okay. You can get rid of Moodle and copy. The access of file on Moodle okay? Video all okay? Okay, so this one. So